Sakura. Okay, so just check Sakura. So there it is in detail described. Okay, so now let's look at the time evolution. You can see now time evolution will be actually a rotation. Okay, so we'll see the time evolution of this in case in presence of the field. Okay, so let's try to understand it. So let me write. Okay, suppose if you are having. Okay, so we start with, let's say, with a spin half particle subjected to the magnetic field, to an external magnetic field. Okay. Okay, so let's call the external magnetic field to be. Clear? So now tell me, what is the interaction energy? So it is the dipole moment due to the spin angular momentum they're dotted with the external magnetic field. So in other words, the interaction energy I can write as the Hamiltonian. So it is minus E by MEC, where Me is the mass of the electron. Okay. So S dot. Clear? So now let me assume, so this is a quite general thing. So B can be time dependent. Okay. So B can be constant. So let's consider a constant field along z direction. So you consider now constant field along z direction. Okay, so what does that mean? So your vector B is actually 0, 0, B. So therefore your Hamiltonian. So I'll put as, okay, so let's not put as in, let's put as operator here. So this means it is the Hamiltonian. I am not using the caps. Okay, so it's minus, now tell me what it will be? Minus EB divided by MEC. Okay, what is S? So it will be SZ. Okay, so what that is? Minus E. Okay, so now tell me what are the eigenvalues here? So this will be actually our Hamiltonian. Clear? So in case of the external field. Okay, so now let's analyze this first from the physical perspective. This kind of problem. So I am having a spin half particle, and you are applying the magnetic field along z direction. What will happen to the spin? It will align with the magnetic field. Clear? Now, okay, so you are tuning the magnetic field for certain time. So what should happen to this thing? When it aligns, because of its motion, okay, so what it should do? So it should actually presses about that magnetic field. Now let's say if you are having an electron in the hydrogen atom or in a certain atom, okay, so it is moving like this way in an orbit. Forget about spin for the time being. Okay, but there is a spin. Okay, so there is an intrinsic rotation in that very orbit. Clear? Okay, so now when you apply the magnetic field, how it will move? So this will presses about the magnetic field and simultaneously go in the orbit. Got it? Samashima? Okay, so that is what we are trying to see here. Okay. Okay, so now let's look at this. Okay, so this H depends on SZ. Got it? Okay. So it means, so I am having this thing, H and SZ commute. Clear? So that means I can have, so if I take that H and SZ, they commute because SZ commutes with itself. So in other words, it means, so I can diagonalize or measure them simultaneously. Okay? So what does that mean? The eigenstates of SZ are the eigenstates of H. So what are the eigenstates of SZ? Tell me. So eigenstates, okay, so it means eigenstates of SZ are the same as, okay, so eigenstates of SZ are what? Plus minus, is it? Oh, eigenstates I am saying, not the eigenvalues. Eh? So like this thing, eh? Plus means along the Z, plus Z direction, minus means along minus direction. Okay, I have given the matrix representation yesterday. Eh? What plus means and minus means. Okay, So in other words, plus minus are what? Eigenstates of this H as well. Because it is only the SZ. If it would have been, let's say, vector S, okay, then this will not be actually the eigenstates of H, and H will not commute with what? SZ. So let's take this objective, this kind of thing, okay? So let's take this. If you take now H and SZ, so this does not commute. So this H, because it depends on what? So you are in this case, so it is Sx Bx, clear? Sy By plus Sz Bz. Got it? Okay, so Sx does not commute with Sz, Sy does not commute with Sz, but Sz commutes with Sz. So this part does not commute with. It means, so I cannot diagonalize H and Sz simultaneously. समझ आया? So I need to figure then a general state which will diagonalize this H. Okay? Got it? Okay. Okay. Okay, so now I need to figure out what are the energies here. Anybody? So now I will write this H acting on plus. So it will be minus EB by MEC as Z acting on plus. So what it gives me? As Z will act on plus, it will give me plus H cross by 2. It is minus E B H cross by 2 MEC plus. Clear? So this will be the what? So energy. Clear? So then you are having H acting on minus. So what you will get? Minus EB by MEC. So SZ acting on minus. So what that is? EB. So it will be minus H cross by 2. H cross by twice MEC minus. Got it? So you are having now two energies. Clear? So what are those? So E minus and plus. So plus minus. So what is that equal to? Okay. Now tell me what are those? Minus plus. Okay. Isha? So E H cross B divided by twice MEC. Okay. So I am having this H plus minus actually equal to E minus plus minus. Okay. So now you can draw the energy diagram. So what are the levels? So the plus level is here. So this is the plus level with energy E minus, and then you are having what? So E plus with minus. So it means plus is actually the ground state and minus is what? Excited state. Got it? And what is the gap between the two? So what is the energy gap? So difference between the two. So that will be simply equal to EB H cross divided by MEC. So let's define this as H cross omega. Got it? So I am defining this gap to be how much? H cross omega. So let's write therefore. So therefore I will write this H is equal to minus omega. So it should not be minus. So okay. So E is the actually this is E is the charge on electron. How much is that? So it's negative, is it? Got it? So I will call this as E as negative times magnitude of E. So what this will be there? So it will be simply like this thing. Okay, let me write magnitude of E B divided by MEC as Z. How much is that? It is simply omega as Z. Because omega is what? EB, magnitude of E. Yeah? So you should put actually magnitude here. Yeah? Magnitude. Got it? Okay. So this is your Hamiltonian. So it's a Hamiltonian for a two-level system. Okay, you can see. Forget about where from it comes. Okay? So last time I have told you if you have to write the Hamiltonian for a two-level system. Okay, so what you do? You put a diagonal matrix. Clear? So what are the values? Omega 0, 0, minus omega. Because SZ is what? So it is like this thing. 1, minus 1, okay, and omega. Clear? So this is a general two-level system now. Okay? So omega, whether if you put omega like this thing, you can say it is your spin half particle. Clear? Or you can say spin half particle and two-level systems, their every property will turn out to be the same. Whether you are working with the two-level system, that means you are actually working with what? You are working with actually 6.5 particle. Or if you are working in a two-dimensional Hilbert space, it means you are restricted to a 6.5 particle. Got it? So these things are interchangeable. Huh? Got it? Okay. So now this is your your two-level system. So now let's look at the time evolution. Huh? Okay. Okay, before let me comment one point here, a remark. So let's look at information. Huh? What is the unit of information? Bit. Is it? So let's say if you have to store information, how you do it? So you store it in units of bits, 1 bit, 2 bits, and so on. Okay, depending upon how big your number is or how big your text is. Okay, so that will take that much of information. Okay, that much of storage will be there. So depending upon how much you want to store in terms of these bits. Clear? So how we represent these bits? It is either 0 or it is actually 1. Okay, got it? So what does that mean? So you are having only, so you can store information in terms of zeros and ones. So you can think, let's say a square wave. Let's assume classically you are having a square wave. Okay, so the lower level is actually 0 and upper would be what? A 1. So this is actually the mathematical way to think of this 0 and 1. Clear? And you store, let's say if you have to on those CDs, okay, DVDs, how you store it? You are actually magnetizing that material, okay, such that the material is divided in such a way you will be getting what? These either zeros or ones. Okay, so let me give you this way. Let's say you are having these 6.5 particles. Clear? So you can magnetize 6.5 particle. Either it will be along the up direction or it can be in the down direction. Clear? So let's think these are independent things. So let's think a material made up of these objects. So that means you can magnetize either what? Along up, all the spins will point up, or all the spins can point down. So now let's say if you have to create zeros, ones, a string of zeros and ones. Clear? So that means you are magnetized in such a way that your particle gets aligned at a position, let's say 1 in the up direction and the position 2nd in the down direction and so on. Let's say if you have to write this thing 0 0 1 1 0 0 1 1 1 so on. Clear? So what does that mean? You need to magnetize a material, clear, in such a way that the physical system, okay, represents your 0 0 or 1 1 so on. Clear? So this is an idea behind representing the bits of the information. Clear? Okay, so now, okay, so if you look, okay, so you can think the two states of a system. Clear? So you are having 0. Let's think of a square wave. The bottom is actually the one state and the top is what? The another state. Clear? So you can think this bit 0 and 1 as a two-state system. Now the point is that can I do the same kind of analysis with the information storage, okay, using the quantum mechanical systems, or do I have a quantum mechanical analog of representing the bits of the information? Clear? Yes. Got it? So we need to figure out what is the quantum analog. Now look here. In quantum mechanics, let's take this very spin particle. Let's spin half. So it can be, you can align it along one direction. You can align it in the opposite direction. Let's say along the z direction or the minus z direction. But there is a possibility this vector, this spin vector, can exist in arbitrary superposition of all these states. So if you see, we have seen before. So we can write this state of a spin system in the arbitrary superposition of what? Up and down state. Plus and minus, ups and downs. So that means I am having infinitely many possibilities to represent this kind of state. So either you can be having a state along the z direction, or you can be having entirely along what? Minus z direction, or you can be having actually linear combination of the both. Because this is the quantum mechanical viewpoint, superposition of the both. So although it is okay, so basically it's only a two-level system. Okay, it is having only two possibilities. So that means this kind of system or this kind of state should represent me a bit of information. Okay, so we call this bit as a qubit. Okay, so which can be having both zeros and ones, or an arbitrary superposition between zeros and ones. Such state we call as a qubit. So we can write the unit of information, unit of quantum information, okay, by qubit. Okay, a qubit can be any two-level system. Okay, so it is actually Q means quantum. It's a quantum bit. Okay, okay. Clear? So now any two-level system will represent your what? A qubit. Let's think of, instead of here spin half particle, think of a polarization of a photon. You can polarize photon in two ways. Let's say only two polarizations are there. So let's say you are having a linear up or linear down, clear? Or circular right or circular left. So these are the possible polarization. Elliptical right, elliptical left. Got it? And you can take polarization at 45 degree and its opposite. Got it? So you can polarize photon only in two ways. You can be having only two polarization. So that means it represents your what? A two-level system. Got it? Effective Hilbert space turns out to be two-dimensional. Okay? Okay, so I can take polarization states to be the bits of the information. Okay? So I can call photon, polarization states of the photon is also a candidate for a qubit. Got it? You can bring a spin half particles, any spin half particle that will act as a qubit. Okay? You can have polarization states of the photon that will act as a qubit. Another way to understand this bit. First, let's understand this bit more in another way. So let me toss a coin. Is it? So how many possibilities are there? So there are two possibilities. But when I toss a coin, so what I will get? At a time, I will get only one, either head or tail. What does that mean? So getting an information of either head or tail. Okay, so that possibility that will represent your bit. Okay? No, bit. So I am taking a coin. So when you toss it, okay, so you get an information of, say, let's say head. Okay, one of the possibilities. So the amount of information you gain, okay, just figuring out one side of a coin, so represents your one bit of information. Okay, so this is a classical example. Got it? Okay. Okay, a quantum mechanical analog is kind of this thing. You cannot put quantum mechanical this way. So once I will take the measurement postulate, then I will take how to extract information from this very state. Clear? Okay. So how is this makes this quantum computers very fast? Wait. So everything comes on time. Okay.
Sir, हो गया time. 10:26.